The symbol, a double-headed arrow, is used in chemical equations to indicate a reversible reaction, meaning that both reactants and products are formed simultaneously. This symbol signifies that the reaction can proceed in either direction, and that a state of dynamic equilibrium can be reached. In chemistry, a closed system is one in which mass is conserved inside the system, but energy can enter or leave the system freely. An open system is one in which both energy and matter can be exchanged between the system and its surroundings. A reversible reaction is one in which products can be converted back into reactants. Dynamic chemical equilibrium refers to a reversible reaction in which the forward and the reverse reactions are taking place at the same rate, and hence the concentrations of reactants and products are constant. Le Chatelier's principle states that when an external stress, such as a change in pressure, temperature, or concentration, is applied to a system in dynamic chemical equilibrium, the equilibrium point will change in such a way as to counteract the stress. Factors affecting equilibrium include concentration. If the concentration of a substance is increased, the reaction that removes this substance will be favored. The concentration of a solid or a pure liquid cannot change, as this is given by the density of the substance. So, if a solid or a pure liquid is added to a system that is in equilibrium, there will be no effect on the equilibrium position. Consider the equation CO2 plus H2 in equilibrium with H2O and CO. What will the effect on the equilibrium be if CO2 is added to the system? The forward reaction is favored. Water and carbon monoxide will increase, hydrogen will decrease, carbon dioxide will eventually decrease. Carbon monoxide is added to the system. So, what happens next? Well, the reverse reaction is favored. Consequently, water will decrease. On the other hand, carbon dioxide and hydrogen will increase. And eventually, carbon monoxide will decrease. Now let's consider what happens when hydrogen is removed from the system. In this case, the reverse reaction is favored. This means water and carbon monoxide will decrease. Meanwhile, carbon dioxide will increase and eventually, hydrogen will increase as well. Finally, let's see what happens when water is removed from the system. Here, the forward reaction is favored. As a result, carbon monoxide will increase. On the flip side, hydrogen and carbon dioxide will decrease. Eventually, water will increase too. Temperature. Heating the system, or an increase in temperature, favors the endothermic reaction. Cooling the system, or a decrease in temperature, favors the exothermic reaction. A positive delta H value means that the forward reaction is endothermic. A negative delta H value means that the forward reaction is exothermic. For the reaction nitrogen gas plus 3 moles of hydrogen gas in equilibrium, with 2 moles of ammonia gas with a delta H of negative 23 kilojoules per mole, what would be the effect if the temperature in the container was increased? Well, an increase in temperature favors the endothermic reaction, which in this case is the reverse reaction. As a result, ammonia will decrease as nitrogen and hydrogen increase. For the reaction carbon dioxide gas plus hydrogen gas in equilibrium with water vapor and carbon monoxide gas, with a delta H of positive 241 kilojoules per mole, what would be the effect of an increase in temperature? An increase in temperature favors the endothermic reaction, which in this case is the forward reaction. Consequently, ammonia will increase as nitrogen and hydrogen decrease. Pressure, it only applies to gases. The pressure of a gas is the result of collisions between the gas particles and the walls of the container. An increase in pressure favors the reaction that produces the lower number of gaseous moles in total. Conversely, a decrease in pressure favors the reaction that produces the higher number of gaseous moles in total. If the number of gaseous moles of reactants is the same as the gaseous moles of products, there will be no effect on the system. For the reaction nitrogen gas plus 3 hydrogen gas in equilibrium with 2 ammonia gas, what would be the effect of an increase in pressure? An increase in pressure favors the reaction that produces the lower number of gaseous moles in total, so the forward reaction is favored. As a result, ammonia will increase while nitrogen and hydrogen will decrease. For the reaction C solid plus CO2 gas in equilibrium with 2CO gas, what would be the effect of a decrease in pressure? A decrease in pressure favors the reaction that produces the higher number of gaseous moles in total, so the forward reaction is favored. Carbon monoxide increases and carbon dioxide decreases. A catalyst affects the rate of both the forward and the reverse reactions equally, so it has no effect on the equilibrium position. However, equilibrium is reached more quickly and at a lower temperature. The common ion effect is used to describe the effect on an equilibrium involving a substance that adds an ion that is a part of the equilibrium. A saturated solution is one in which no more solids or solutes will dissolve. The solute ionizes. Therefore, if a compound is added to a system in equilibrium and it contains an ion already present in the equilibrium system, then the reaction that uses up that ion will be favored. Consider the following reaction. PbCl2, solid in equilibrium with Pb2 plus aqueous plus Cl aqueous. What would be the effect on the equilibrium if Pb, NO3 is added to the system? Lead nitrate, Pb, NO3 has lead Pb2 plus ions, which are the common ions. The reverse reaction is favored and chloride ions will decrease.